The speaker is James Wagner. He will talk about a universal carving approach for database forensic analysis.
Hi. So along with my name on the title slide, I have my advisor here at DePaul, Alex Rosen, and our industry collaborator, Jonathan Greer. So to give you an overview of what I'll talk about today, first I'll give you some background into database forensics, and I'll talk about what separates database forensics from traditional file system forensics. Next, I'll talk about how to reconstruct database data and the tool that we use to do that. And then I'll go into more detail about how to reconstruct deleted data. Then I'll present some experiments, and finally I'll talk about some future work. So to access files, file systems store the physical address of files on disk. This also includes fragmented files, so files can be fragmented in 2 or 3 pieces. Now, file carving is the technique in file system forensics of reconstructing these files without any of the file system metadata. So you're going to reconstruct these files without actually knowing the addresses. And this is typically done by searching for file headers and file footers. And the scenarios where you would want to use this is, say you have a corrupt disk, or you need a read-only technique to reconstruct the data. So if you're a forensic investigator, any cross-contamination is going to compromise your evidence. So if you accidentally write something that's even not related to the data of interest, you still can't guarantee that you never affected the data. Now, it turns out database forensics becomes a lot more complex than file system forensics. This is because each database has its own specific storage model. Database files don't have a file header. Records across the entire database aren't going to have the same structure, and values are often encoded with metadata. I also want to reiterate that forensics is reconstruction and not recovery. So recovery implies that your database is still alive and you have some type of planned backup. However, in forensics, we require no database intervention. We assume there's no backups available. And again, the scenarios would be if you have a corrupted disk, you want to reconstruct deleted files, or you need a read-only method. So I mentioned one of the challenges of database forensics is that records aren't going to have the same structure across the entire file. So for example, take table customer and table supplier. They each have different attributes, and they store different data types for each attribute. This gets even more complex when you consider other database structures, such as indexes or materialized views, where an index is used to speed up query access, and they store value pointer pairs, and a materialized view stores a pre-computed query result. So on this slide, I have a materialized view that stores name and account balance for all account balances from table customer greater than 3,000. So to simplify this problem of record reconstruction, we're going to look at database storage at the minimum unit, which is pages. And pages are typically 4 to 8 kilobytes, and this is for efficient read-write access and memory utilization. I also want to mention that in a page, you're only going to store data for one structure. So I'm either going to store table customer or table supplier in a page. I'm not going to store both. I'm not going to store a table and an index. It's just one structure. Now, we found for across all databases and all database structures, pages share 3 properties. Page header, which is going to contain information about what structure it belongs to. So for example, table customer. The row directory, which stores a list of pointers to each individual row within the page, and the row data, which stores the rows themselves along with some metadata. Now, some databases may store other structures related to transactions, but we're not concerned about that in this work. So our overall goal is to reconstruct these pages, and we want to generalize that process for all databases. And to do this, we developed our tool called Database Image Content Explorer, or DICE. So DICE is broken up into 2 components. You have the parameter detector and the content parser. Now, the parameter detector is going to load synthetic data into the database, capture database storage, describe page layout with a set of parameters, and write these parameters to a configuration file. The parser is then going to use these configuration files to reconstruct pages from any type of file passed to it. So you could pass disk image, memory snapshots, and then it's going to output data that can be accessed by the user, such as tables, data that can't be directly accessed by users, such as indexes, and deleted data. So real quick, the reason why we decided to develop DICE in Python is, again, we wanted to make this database agnostic. We wanted it to work for every database. And we found that every database offers an adapter for Python. We also want to make it OS agnostic, and Python is portable across all operating systems. Database connections are simple in Python, typically just one line of code. And when we first started developing this tool, we were constantly changing and creating new parameters, and this requires comparing data across thousands of pages and records, and this type of data analysis really isn't feasible for one person to do in a language like Java or C. So as far as parameter collection goes, we found for the page header and the row directory is fairly straightforward. You're trying to locate IDs and pointers and describe how to reconstruct them. And it turns out this is very similar across all databases. Now it gets a lot more complicated when you get to the row data. So for example, I have up here on this slide 3 possible layouts that a database may use for row data layout. I'm not going to discuss all these parameters. I just want you to get an idea of how complex it can be. Some of the parameters that are interesting are you may have a row delimiter to separate each row. You may store the size of each column. And then if you don't store the size of each column, you may use a column directory, which is going to store pointers to each column in that row. And then another example of how complex the row data can be is primary key storage in MySQL. Now, primary key is used to uniquely identify a row in a table. And we had somebody from industry contact us about reconstructing deleted data from MySQL. And the data set he gave us that he was trying to use to do this didn't contain a primary key. Well, the problem is when you do create the primary key, it's going to change storage. So that column is actually going to be stored differently from the rest of the row. So he would have been in for a big surprise when he went up against real world data. Another problem is data types, so reconstructing these. An example is integers. So in Postgres, it wasn't too big of a surprise. Postgres actually stores numbers like pointers or IDs are stored. It represents a number with 4 bytes, and it can be decoded with that equation I have up here on the slide. And then I have 3 example numbers. However, Oracle uses zero compression to represent numbers, and there's no obvious way to automate this. So I have 4 example numbers that Oracle uses. Those are correct. It's very odd. So the first byte represents the number of bytes needed to store the number. The second byte is a zero compression dictionary key, and any following bytes represent 2 digits of the number, but it's that number minus 1. So for the first number, I have a 5, but that actually represents a 4. The second one is a 41, but it actually represents a 40. And then you get into the zero compression. So another problem is data type detection. So is what I'm reading actually a number or a string? And again, in Postgres, this is one of my favorite examples. So I told you Postgres uses 4 bytes to store a number. Now, Postgres also, for a string, is going to store the size of the string before the string starts. So if I have a 3-byte string, I'm actually going to use 4 bytes to represent that string. So it's hard to say with certainty what I'm actually reading, if that's a string or an integer, because I can plug it in to that equation I have up there if it's a string still. So I have to make a few assumptions about this. For example, I assume that you can't have the ASCII null value or decimal value 0 in a string. So for all the parameters that I was talking about, it turns out there's a lot of overlap between databases. Again, the most interesting is when you get into the row data. So a database is either going to store the size of columns or it's going to use a column directory, which is going to have pointers to each column. And if it stores the size of the columns, it's going to store numbers and strings together, so in the form that you created the table. However, if you use a column directory, it's going to store numbers and strings separately. So at the bottom of the slide, I have an example. On the left, we have John Smith and Texas as the strings. I have the sizes stored in front of them, and I have interleaved the two numbers 5 and 11. Now on the right, I have the column directory with pointers to where each column starts, but I have my numbers and strings stored separately. So this slide shows an example of how we use the parameters to actually reconstruct the data. On the left, I have the parameters we're going to use, and on the right, I have a small snippet of a row from a raw data file, and I have each byte represented with the ASCII character and decimal value. Now, there is more metadata before the row starts, and there's more columns that follow, but this is what we need to reconstruct these two columns in this example. So first, I'm going to search for the raw data delimiter with those 3 decimal values. Then I know the raw data starts 4 bytes after that, so I'm going to jump 4 bytes. I'm going to start reading the first row. So earlier I talked about in Postgres, I make an assumption that a string cannot have decimal value 0 in it. So I'm going to assume that this first column is a number. I'm going to decode it, and I get the value 1,579 for the first column. Now I'm going to move on to the second column. So earlier I told you that Postgres stores the size of a string before a string starts. However, it doesn't store the explicit size. So the parameter detector needs to recreate these decoding constants. So I have string variable x and string variable y. So I'm going to decode that 31, and I'm going to get that the next column size is 18 bytes. And this may seem unusual, but there's actually several databases that do this. So once we set this up for one database, it works for all databases. So for example, SQLite does the same thing. So DICE currently supports 8 different databases and several versions for each database, and on both Linux and Windows. So 2 interesting things to point out on this slide is we found that for an older version of Postgres, about 10 or 15 years old, the parameter detector produced a different set of parameters. And also, starting out building DICE, we had to keep on creating new parameters for each database. Well, we eventually got to the point when we ran the parameter detector against Firebird that we didn't have to create any new parameters. And this was the goal of the project. So any new database that we introduce, we want everything just to work and no manual intervention. So now I'll go into a little bit more detail about how to reconstruct deleted data. And again, this is data that's no longer recoverable. I can't roll back. I don't have log files. This is data that's gone, and the user is unaware that it exists. So when you delete data, you just mark the data. You don't overwrite it. The database just recognizes this as unallocated storage space. And we were able to characterize 3 different types of deletes that DICE can reconstruct. You have rows, entire pages, which would be caused by if you delete an entire table or if you rebuild a table, and then values, which are going to be found in auxiliary structures such as indexes. So for deleted rows, we found that 4 of the 6 major databases mark or delete in the row data. So MySQL and Oracle, we're deleting row 2 here in all three figures. MySQL and Oracle mark the row delimiter. Postgres marks that raw data delimiter that we used in the reconstruction example. And SQLite marks the row ID, which is an internal database column that represents the physical location of a row. Now, I left out DB2 and SQL Server because they don't mark the row data. Instead, what they do is they mark the row directory. And remember, the row directory stores a pointer to each individual row in the page. And what they do is they null out this address. So to reconstruct a row in DB2 or SQL Server, you need to consider the address before and the address after and find the structure of a row somewhere in between those two values. Deleted pages, again, these can be created by dropping a table or rebuilding a table. When you delete a table, it's not actually marked within the pages. What you need to do is you need to go back and look at the system tables. And there's one system table that's going to keep a catalog of all of the structures and their corresponding structure IDs. And so when you delete a table, you're actually going to mark that structure is deleted like you would in a row on the previous slide. So if I delete table supplier, it gets marked in the system table. So now I know any page with structure ID 126 is actually a deleted page. So I go back and look on disk and I see 2 pages with the structure ID 126. And I know that these are deleted. Deleted values, these actually have a lot longer lifetime than a deleted row or deleted page. So if I delete the values Carl and Greg, these get marked in the pages. However, in the index pages, I'm not going to actually mark those values. Those values are going to hang around until something causes an actual index rebuild. And this would be something like a high volume of inserts, or the user explicitly issues an index rebuild. So a couple experiments here. This first one is recovering deleted data, or more specifically rows. So DICE has no problem recovering deleted rows immediately after the delete occurs, because again, a delete doesn't actually overwrite the data. It just marks it as deleted. So we're concerned in this experiment about the lifetime of deleted rows. And we chose 2 databases that we feel represent all databases for the lifetime of deleted rows. Now, Oracle uses a % page utilization. So if I have over 40% of deleted rows, I'm going to start overwriting deleted rows in that page. SQL Server, on the other hand, if I delete a row and a newly inserted row can fit in that old space, then I can overwrite that row. So we used 2 tables for each database. For the first table, we issued random deletes throughout the table. And for the second table, we did contiguous deletes in the table. So for Oracle on the random deletes, we never fell below that % page utilization. So we were able to recover all of the deleted rows. For the contiguous deletes, we fell below that % page utilization, and the new inserted rows came in and overwrote the old ones. The remaining values we were able to recover landed in a page that didn't fall below the utilization threshold. Now, SQL Server, on the other hand, quite different behavior. We were able to recover about 40% of the deleted rows over time for the random deletes. And for the contiguous deletes, almost all of them were overwritten. And this is because it's much easier for an inserted row to find unallocated space that's contiguous rather than fragmented. And so to kind of illustrate what's going on here with the random deletes, I have the deleted row supplier 1, Bob. Now, if I insert the row supplier 3 ed, I can overwrite it because it's smaller. And the interesting thing in here is that I still have part of that old row remaining. So that B still remains in the page. However, if I insert the row supplier 3 Gregory, that's too big to overwrite the deleted row, so it gets appended to the table, and that deleted row can still be reconstructed. So another thing you can do with Dice is monitor memory. So each one of these images is the database buffer cache, where each pixel represents one page, and I have a total of 50,000 pages in each image, giving us a buffer cache of 400 megabytes. So what we're doing here is we're issuing queries, and those queries are going to read pages from disk into memory. They're going to flush old pages out. So here you can see I issue some queries from snapshot 1 to snapshot 2. I issue some queries on table customer and table part. And you can see at the bottom that the dark red and the bright red come in and flush old pages out. So again, going from snapshot 2 to snapshot 3, I issue some queries on table line order. And you can see at the top, I have some of the dark green pages come in and flush out some of the old pages. And finally, I issue a bunch of queries on line order to try to flush out memory. Now, the interesting part here is you can still see some old data pages laying around in memory, some of the blue in the last snapshot. So the real question here is, can you reconstruct an old query from those few pages left in memory, and what would be the lifetime of that? How many cycles of flushing the cache can you actually do that? So here's just a summary of those 4 snapshots that I just showed you. So in conclusion, we use Dice to generalize database storage at the page level. This can be used to reconstruct data that's corrupted, deleted, memory snapshots, and when you need a read-only method. So future work for this project, we have plans we want to detect log file modification using forensic analysis. Now, this would be the case if the database administrator, he has privileges to disable logging, but you want to see if you want to audit the database administrator and see if he's been doing anything suspicious. So we can go back onto disk, decide to reconstruct all the deleted rows. If we see a deleted row that doesn't match any of the delete operations found in the log files, then we would consider this to be suspicious activity. Furthermore, if we see data in memory that doesn't match any of the stored queries, then we would also flag that as suspicious activity. And any questions? Yes. That's a good question. If you talk to me afterwards, I could probably provide you a prototype, but we don't have open source. We plan to go open source, but it's not open source quality yet. So, I mean, Dice just, as long as you pass it a disk image, it's going to be able to scan that image and reconstruct any possible database that was on there. So the disk image is in most cases, do you want the physical disk? I mean, we just need a copy of, we just need an image of it. It's. That I am not familiar with that process of what. Right now, we've just taken images of Amazon EC2 virtual machines. We haven't actually imaged hard drives from like a computer, but it would. Not necessarily.
I will help repeat the questions because the recording has only you guys.
So you don't necessarily need a VM. It could be any disk image. Yeah. Not necessarily.
Any more questions? Okay, no speaker. So we have our coffee break now. And press the button. Perfect. Cool. Oh, nice. Nice tool. So working low level with Python on the images, how was reading sector and everything?
Yeah. It took a few months to get the first database down, but once we got the first one down, it was
Yeah,
quick to
it was.
add in. Yeah.
Yeah, nice. I never